So, hi, my name is Devon Stewart. I work out of San Francisco at a company called Twilio. Recently we had an opportunity to use ScalaMeta for a great reduction in boilerplate internally on our Akka HTTP codebase. So today I would like to talk about some of the strategies and lessons learned from working with ScalaMeta in the real world. This is also going to be an interactive presentation. You might notice that this looks a lot like SBT, or the Scala console at least. So if any point during this presentation you have a question, please immediately raise your hand, because this talk is going to be somewhat technical. I've done my best to try and make the code as straightforward as possible, but the code itself is going to be a combination of runtime, and also what is going to come out of it is going to be the generated macro code. So that's also assuming that you know what ScalaMeta is already, so I'll start with that. This is what we're going to talk about is why we needed metaprogramming. And then just a brief introduction into Swagger specification of an API. And then how we, like a simplified use case of how we generated code from a Swagger specification. Then going to be playing around in the terminal a little bit with packing and unpacking quasi-quotes, because that was extraordinarily helpful to learn and become familiar and comfortable with ScalaMeta. And then at the end, we'll have some time for questions. So let's get started. So this is a simple specification of an API, HTTP API, that gets a user from some backend service by its ID. The implementation here is not so important, but this is generally the structure of data that we received from our service providers. So the people who wrote these or generated these API specifications gave us many specifications like this for different services. And we were able to use ScalaMeta to completely dynamically generate our code that talked to these services on Akka HTTP. So the end of the presentation right now is we had a great success and it was good, and so let's look at it. So initially, I'm going to unpack this API. I'm going to pull out some values that we will use later. So the scheme and host for HTTP. The first path specification, so the template that we saw earlier for user and then in brackets ID. And then the operation that we're going to actually perform can be extracted further. We're going to call this operation getUser in the generated library. And then we are going to handle the response type automatically using Circe decoders. So Circe from type level. So that will decode a user class. And the user class is just, it's defined outside of the slides, but it is just an ID, a username, and an age. So initially, what I found very helpful to do is to write the desired output of this experiment. So writing in plain Scala the exact function, word for word, that you want to get out of ScalaMeta was actually a very good place to start. Because what we ended up doing is we took this and we started making it dynamic piece by piece, which was very easy to do using ScalaMeta. So we are going to import ScalaMeta here. If you're trying out ScalaMeta in the SBT REPL, just a note is that ScalaMeta conflicts with the previous meta library, so you actually have to do this strange thing in order to get the slides to work in SBT console. So yeah, that was interesting to find. So this is the general structure, spaced out a little bit so that as we step through the slides, we can see how the code changes from slide to slide. So also a reminder is, please, if you don't understand or if it's not clear exactly how things are changing between slides, please ask immediately because we can go back and forth. So this is just the same code from earlier, the code that I want to receive, but spaced out so that when we, for instance, start replacing the values, we're going to actually fill in the rest of the code. So I start by creating this goal object. Goal is our desired function that we create. And I can actually look at it in the REPL here. I cannot. I can do this. And that will generate the meta definition. So you can actually see the type there is a definition def. There's actually many different. The ScalaMeta type hierarchy is sort of, I guess, intimidating initially is the easiest way to represent it or to talk about it. But if we look at the actual code, this is actually what I found to be the most straightforward way to understand how the types worked. There's just one file in ScalaMeta source code called meta.trees, or metatrees.scala rather. And it has, I think, every single type. I haven't found a type yet that isn't in this file. And understanding the hierarchy of these types is extremely important if you will be working with ScalaMeta. For instance, the difference between a parameter name and a type name, ScalaMeta makes a distinction. So the distinction will cause definitely compile time errors, but also if you're using the runtime variants of ScalaMeta, you could get runtime errors if you are not very careful with what you're doing. It uses reflection under the hood, so for that reason, it's good to be very aware of how these pieces fit together. So going back to the slides. So I have this definition, which is very nice, but what's actually even cooler, I think, is I can extract using normal unpacking pattern matching using ScalaMeta. I can actually extract even something as complex as this entire function definition. Because if we look at how goal is structured, the structure of goal is actually just this kind of nested sequence of abstract syntax tree elements, or AST elements. So if you think about how case classes can be unpacked nested, this is actually the same thing. So if any of these pieces are missing, but the rest of the structure matches, you can unpack, I think, anything. That might not be entirely true, but I haven't found something that doesn't unpack yet. So if we run this code, we should see, hopefully it won't explode. Oh, we see nothing. But that's good. This is because there's actually nothing, there are no template values in this slide. So that's a sign that everything matched, and because we did not create any new values, we didn't get anything back. So I call this a success. Next slide. So we're going to start by turning this single ScalaMeta definition into a function that we will eventually give parameters to. So here I have the question marks. And then as we start pulling out static values from this function into those parameters, you will start seeing that the function becomes more dynamic. And as it becomes more dynamic, we can use that function in many different capacities to build different implementations of this same structure. So different methods or different paths or different return types, all just using this same structure. So the first one that we're going to pull out is the scheme, the HTTP scheme. So let's look at the difference here is the value. Because this is a quasi-quote, it works very similar to string interpolation in the sense that dollar scheme here, that actually is now pulled in from your parameters of this function, but it is a literal in ScalaMeta because we actually want this to be just a plain string, and a string is represented as a literal. So if I pass in a literal value, that literal value will be interpolated into this function as it's being rendered. So then we can continue extracting the host very similarly on the same line. We have the exact same thing where we can talk about the addition of these literals, so it's like string concatenation of scheme plus colon slash slash plus literal, so but plus host. But if we look at what this used to be, right, this used to just be strings. So we can actually think about, in the future, once this is all rendered, it will just look like that string. So we can do anything on that string that we could normally do. So we're going to next replace the path template. Now the path template additionally, actually accidentally is missing a $sign. Sorry about that. But the path template here should have a $sign in front of it. It should behave like a normal string when we use that thing. It's going to it's going to be replaced, and then the .replace method will be called on that replaced string once that interpolated string is there. So it's going to go away soon, but the next one that we replaced is the operation ID. The operation ID is actually the name of this function, is a term name. And so now we have actually abstracted even the name of the function. So we can generate all kinds of different functions with different names just by calling this one build method function with different parameters. So we're getting close to fully abstracting this function. So continuing, the body type, the type that we're going to be extracting out of the response type is this, it's actually just a type. So the body type shows up in a couple of different places in this code. So you also have it down here once we start trying to decode the response type coming out of Akka HTTP. So because that is it's a type value, you can create them just using the T string interpolator, or the string quasi-quote interpolator context, string context, that's what it is, sorry, string context. So I can actually say user, and I will get back a type that I can pass into this function at that, in that argument. So I can actually provide any type that I want to just by using that, that quasi-quote. Or you can actually just use like type name user constructor. So both of these do the same thing. We found that there's sometimes you can't use string interpolation because string interpolation only works with literal values in all contexts. So sometimes you actually end up running into a situation where your name is, let's say, user. And then if I wanted to have like a function definition, I could actually, well, I'll just use the quasi-quote here for function literal, term name. And I can't actually do this, pretty sure. I was just trying to do this, yeah. So it will try to pick the right type that comes out of the quasi-quote, but it's only guaranteed if the type is very specific or very well known. So sometimes you will find yourself not able to use quasi-quotes. You will have to switch back to using the normal constructors. But for the most part, they work very interchangeably, so you can actually jump back and forth between them. So whatever is most convenient for what you're trying to write should be used, because it's good. So going back to the slides. We're going to also replace whoa. Oh, did I really just, I did, ooh. Sorry, 1 second. Not that one. Oh, hey there. So, this is why good variable names are important, because then you don't end up doing that. Pres n. So, next. So we are going to go to the next one. The next one is the parameter list. So this one's actually the fun one. This is this is where it takes a little bit more concentration than the other ones. Please ask questions. We've replaced all of the parameters that come into this function with a single extractor. So this is the dot actually takes all of the arguments and puts them into a sequence. And then we want to use those parameters later in the function. So we actually want to do what we were doing before with this path template, but we want to replace arbitrary parameters that you pass in. You don't want to have to specify them all in your function, otherwise you have not gained anything. So the dynamic aspect of ScalaMeta here is really that because you have, you can use $open curly brace to create a Scala context inside a ScalaMeta quasi-quote, you can actually nest quasi-quotes. So this was very useful, although somewhat difficult to read, so use it with caution. We constrained the input type, this path template. We constrained that instead of having it being a literal, we constrained it to a term. A term is at least one step up, but that allows us to also use function calls. So in this fold. So we're going to be folding over all of the parameters and replacing them one by one through this extraction, this I guess the transformation. So we're going to look at the code to do that. So a reminder is that we are inside one quasi-quote, so this $open parentheses params is inside one quasi-quote, but then we're going to start another quasi-quote inside to do the replacement on the template. So our initial template looked like this. So our initial template was this user ID. So what we're going to see is we're going to replace the ID with the value of that ID that gets passed into the generated function. So when this function is generated, it will have one parameter, and then we're going to use that parameter in the fold left, the code that's generated from the fold left. Sorry. So what we want to see is we actually want to see something like path temple exists. So I want to see replace ID with the literal ID, whatever that is at the time. So if it's like, for instance, like 7, I want 7 to end up in that interpolation. And because we're using fold, we can actually, if I had instead a path that was more complex, like user ID name first name, like that, the first replace would replace ID with 7, and the second one would be replace first name with Devon. And then we would see the fully interpolated path string. But that, in order to get that level of expression in ScalaMeta, we are going to actually fold we're going to build the resulting expression directly in this style here. So we start with this A accumulator, which starts off as path template, but then we're going to call replace on that. And we don't know what we're going to put here yet. We also don't know what we're going to put here yet. So we're going to find that out now. We are going to pull the parameter name out of this params list as we go through the params. We pull the parameter name and unwrap the value. So the name is just the so the name is a parameter name, but then if you get the value, you can get the string back out. So just a reminder that even though this has a lot of types to represent all of the complexity of Scala, it's actually still usable. You can actually get things out of it without using reflection. You get the same values that you would normally get with the same types. So that was very nice to find. Additionally, we then wrap that in a literal because we actually want to replace the string name, so the parameter name, so ID in this case. We want to replace the string of ID like this, where ID is the parameter name. So we actually have to convert between one type and another type. So we're converting between the parameter name and the literal of the name of the parameter. So we would get that sort of string, and then we would replace on that string. So then we do the opposite. Instead of getting a literal, we now get a term name. So instead of using the string value, now we want to say the real value of that parameter that got passed in. So we can use that in this way to generate a function that looks very similar to what I've written here. And because that's inside of a fold, we will generate that for every single parameter that gets passed in. So in 4 lines, we have generated something that can interpolate absolutely any pattern that you pass in. Any parameter that you give this function will be interpolated into these values. Yeah.
This works only for the string parameters. I mean, because I understand in this case it is string, right?
Yeah. So this is in that case a simplified example, but when we wrote this similar thing, we actually preserved the type by using type classes to handle this ID case. So we actually did something like encode path component. And so because, oh, sorry, was the did the translators get the question? Okay, sorry. The question was, this technique only works for strings. The way that I've written it in the slide only works for strings, but in the actual production code, we were able to use type classes to mitigate that restriction. So
The reason that I ask is because probably, I mean, in the generic case, you would probably need to also interpolate the type parameters before the dynamic extraction. Because, for example, you have a generic that one of the parameters is of type T, and then you will need to have the, let's say, square brackets for the type before the.
it's possible. I'm sort of following, and also I'm trying to remember what I can say to the translators.
Sorry.
It's okay. Yeah. Yeah. So the initial question? Yeah. 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 So the original question was just that it seems like this code only handles the string case of string-typed parameters instead of being able to handle any kind of parameter passed in. And the answer is yes, this slide has been simplified, but the code that I wrote on the bottom here is closer to what we ended up with using path component. Because the types are preserved in the generated code, even though we did not have access to the types in this case, we didn't use the types. We had access because the types are in this parameter, but we did not use those types here. We relied on the compile time of the client. Once this code was macro generated, then when it was compiled again, at that point we had all of the types present, and we could use a type class to handle any arbitrary types. So we had a large number of different types that had type class instances for them. I'm interested in expanding that to anything that can be decoded by Akka, which would make it much less boilerplate and also be able to reuse existing code. So that's something that I'm interested in doing. So onward. So whoa. Oh, you got the last slide too. But if we run this one, we can actually see that we get from this, we get our initial method back. We actually get the first, like the get user. If we're, actually, sorry, I'm gonna scroll up here. So if we're looking at this, these are the initial values that we pulled out of the Swagger template. So scheme, host, path template. And then this one, I cheated a little bit, sorry. But I can show you more interesting code after if you have further questions. But this, I'm using most of the stuff that we pulled out of this Swagger generation, or the Swagger specification, and I used it just now to generate this function, which you can see has our scheme, host, we've got the return parameters, and we actually decode that using a decoder generated by Circe for the type that we passed in. So because of this, that one function is now capable of handling any input that you could give that Swagger specification entirely generated using ScalaMeta. So continuing to build on this, to build a true library that encompasses all of the functionality is actually doable. And I think, based on my experience, many people could work on this at the same time without running into issues where multiple people are trying to do different things with the code because the types are there, the types are well expressed, and it does not rely on string interpolation or reflection. It's all kind of construction. So that's, I think, the major differentiator for me, and also I think my team, between this implementation, even this simple implementation of a Swagger code generator versus the official Swagger code generator that actually just uses mustache templates and string concatenation. So I think this as a technology for me is very exciting, and I hope that you also are excited. So thank you.